Hi everyone, and welcome to the first of 4 videos going through some past exam questions on the topic of intermolecular forces. So this first question here is asking us about the halogens. These come up quite a bit when we're talking about intermolecular forces. And it says here that halogens have van der Waals forces between their molecules. Okay, now this is a question from the old spec. They won't use the phrase van der Waals forces. It's probably one you may not be familiar with. If you look for any old questions, if you find them online or if you're looking through old textbooks or websites or things, they might use the phrase van der Waals forces. The exam board will now use the phrase London forces, which hopefully you're familiar with and will be in your textbook, and that's what they will use on the exam. So if you see anything about van der Waals forces, you want to be thinking London forces here. So it says halogens have London forces between their molecules. Describe how London forces arise. Okay, so London forces are temporary dipole-dipole interactions. Okay, they don't exist all the time. The reason that they come about in the first place is because you have the electrons constantly moving within the molecules. Okay, so that's the first thing we want to say. Electrons in halogen molecules are constantly moving and may become unevenly distributed. Okay, that's the first thing that happens, right? Because these electrons are constantly moving about in their orbitals, just by chance, at a particular, if you take a snapshot in time, there's no reason why the electrons would be spread evenly across the molecule. Okay, just purely by chance, they might be unevenly distributed. We might end up with more electrons at one end of the molecule than the other. Okay, that's going to have consequences. The end of the molecule that has got more electrons is going to end up with a slight negative charge. Okay, and the end of the molecule with slightly less electrons is going to end up with a slight positive charge. Okay, so if the electrons become unevenly distributed, this is going to create a temporary dipole. Okay, and it's only a temporary dipole because the electrons are constantly moving, right? So as soon as this dipole gets set up, then the electrons will move again, and then that dipole will go away. Okay, it was only there because the electrons were unevenly distributed, because they were more up one end of the molecule than the other. If they then move, well then that dipole is no longer going to exist. It might set up a dipole the opposite way around. Okay, but then that won't exist for very long. It'll go back to how it was before, or it'll go back to having no dipole. So you've got this constant state of changing between we've got a dipole, we've not got a dipole, now the dipole's the other way around, because those electrons are always moving. Okay, so this is why you get a temporary dipole, and this is why London forces is such a weak force, because it's not even there some of the time. Okay, so we're going to get 1 mark for talking about the electrons being unevenly distributed, 1 mark for talking about the temporary dipole, but we still need 1 more mark here. This is a temporary dipole within a halogen molecule, right? And it's saying that one end of the molecule is positive and one end is negative, but this is an intermolecular force between the molecules. So we need to explain why is there an attraction between one molecule and the next. Okay. What we can then say is that a temporary dipole in one molecule will induce a dipole in the neighboring molecule. So it's this idea that once you've got one molecule which is slightly negative at one end and slightly positive at the other, then the negative end of that molecule will repel all the electrons in the neighboring molecule. And so they'll go down the end furthest from the original molecule. And so that second molecule will then also have a temporary dipole set up in it. Okay, and then the two molecules will attract each other because of their dipoles. Okay, so it's this idea of one molecule inducing or creating a dipole in the next molecule, and then the two molecules will interact with each other. So then it says state and explain the trend in the boiling points as we go down the group. Okay, so the first thing we want to do is state. We need to do what it says, state and explain. So let's state it first. Okay, as you go down the group 7, the boiling points increase. That's something that we need to know. But why? Okay, well, it must be to do with the London forces. We've just been talking about how halogen molecules have London forces as the intermolecular force between the molecules. So if the boiling points are increasing, then what does that tell you? It tells you that the London forces must be stronger as you go down the group. Okay. Okay, so this is because the London forces become stronger. Okay, but why is that? Why are the London forces stronger? Where do the London forces come from? From this idea of the electrons being unevenly distributed. The further down the group we go, the more electrons they have, right? Because we've got extra shells. The more electrons you've got, the more unevenly they can be distributed. If you've only got 2 electrons, then the most uneven it can be is 2 against 0. Okay, but if you've got 50 electrons, they could be much more uneven. Okay, so the London forces become stronger down the group as the halogen molecules have more electrons. And then there's one other thing we can put here. We probably would get all the marks for this. It's a 3-mark question. So we get 1 mark saying they increase, and then the London forces become stronger, and then because they've got more electrons. But it's always a good idea. There's usually an extra mark, just in case one of these points doesn't count as a mark. That if you're talking about intermolecular forces, if you said you've got stronger intermolecular forces, there's usually an extra mark available for saying, therefore it takes more energy to break them. Okay. So we can say the stronger London forces require more energy to overcome. And that's why we end up with a higher boiling point. Okay, so that was all about London forces, but there are other types of intermolecular forces. Okay, and these questions here are going to focus on hydrogen bonds. Okay, so here we've got, it's talking about water. Water has got hydrogen bonding. Complete this diagram to show hydrogen bonding between the H2O molecule shown and one other H2O molecule. Include relevant dipoles and lone pairs. So this is nice. It's basically telling us what to do. Okay, so we need to put dipoles, we need to do lone pairs. Right, well, the oxygen is going to have lone pairs, and it's going to have 2 of them. So here's a lone pair, here's another lone pair. And then the dipoles, oxygen is more electronegative than hydrogen. So the oxygen is going to end up delta minus, and the hydrogens are going to be delta plus. What's going to happen then is there's going to be a hydrogen bond between this molecule and another molecule. And so the negative oxygen is going to be attracted to a hydrogen from another water molecule. Okay, and so again, let's put the lone pairs on the oxygen here, and let's put the dipoles on here. So then this oxygen is going to be attracted to this hydrogen, but we want to be specific about it. They've specifically said show the lone pairs, so that's where the attraction is going to be. This hydrogen is going to be attracted to the lone pair of this oxygen. Okay, so here's going to be the attraction. Okay, and this is going to be our hydrogen bond. Okay, and they will get picky about this, that you want to show the hydrogen from one molecule being attracted to the lone pair of the oxygen, not just to the oxygen, but specifically to the lone pair. Okay. Right, why do hydrogen bonds matter? Okay, because they give water some unusual properties. Okay, in this case, they're asking for properties of ice. Just be careful here. So the first thing that we can talk about is that ice actually has a lower density than water. Which is unusual, right? For a solid to have a lower density than a liquid, that's unusual, right? There's not many other substances you can say that about. So, and then explain it. So why is that the case? Because hydrogen bonds hold the molecules further apart in the solid lattice. Than in the liquid. So it's this idea that in the liquid, the molecules are constantly moving around, so they're jostling each other, they're getting close together, they're going further apart again. Whereas in the solid, they're fixed in position, and they're fixed in position by the hydrogen bonds. They're always this distance apart. Okay, whereas on average in the liquid, they're actually closer together because the hydrogen bonds are breaking and reforming between different molecules all the time. Okay. And then the second point, it has to be, this is where we need to be careful, it has to be a property of ice. So we don't want to say water has a high boiling point because it's got to be a property of ice. We need to talk about the melting point. So ice, and we don't want to say ice has a high melting point because it doesn't, does it? It melts at 0 degrees. You can't count 0 as being a high melting point. But it has a higher melting point than other similar molecules. Okay, it needs to be this kind of, we need to qualify what we're saying here. It needs to be a comparison. It's not high, okay, but it's relatively high compared to other things. So it's got a higher melting point than other similar molecules because hydrogen bonds are relatively strong intermolecular forces. Okay, they're certainly stronger than permanent dipoles or London forces. So this is why we have higher melting point than we'd expect. Okay. Then it's asking us to do ammonia. Ammonia is also going to have hydrogen bonds. Remember, you do need to be careful. We're talking about hydrogen bonds. You only get hydrogen bonds with fluorine, oxygen, and nitrogen. Okay, those are the only 3 elements. So NH3 is going to form hydrogen bonds. Draw a diagram to show the hydrogen bonding. Okay, so this is very similar to the question we did already, but we've got to do it with NH3. Okay, so let's draw an NH3 molecule. Okay, we wouldn't have to draw the shape here. Okay, they're not going to mark us down for drawing it the wrong shape, but we might as well try to do something the right kind of a shape. I'm trying to show this pyramidal shape here. Okay, and then our nitrogen is going to have a lone pair. Okay, I'm drawing it off at an angle here because I want to try and show it being attracted to the hydrogen here. Let's put a lone pair on here as well. So again, we want to make sure that the hydrogen bond, let's label it. It doesn't say to label it, but it's probably a good habit to get into. We want to make sure the hydrogen bond is going to the lone pair. Okay, same as we did with the oxygen on the water. And then we also need to show the dipoles. The nitrogen is more electronegative than the hydrogens. Okay. Right, and then finally, suggest why ice has a higher melting point than solid ammonia. Okay, well, if it's got a higher melting point, it must be because the intermolecular forces are stronger. And in this case, it's going to be the hydrogen bonds, right? So it must be that the hydrogen bonds in ice are stronger and therefore take more energy to break. The hydrogen bonds in ice are stronger than those in solid ammonia and take more energy to break. Remember we said it's usually worth putting that in if you're talking about intermolecular forces. But why? Why would they be stronger? They're not just going to let us get away with that. We need to come up with some sort of explanation. And there's actually 2 reasons that you could give here. So this is because, well, what determines the strength of a hydrogen bond is the strength of this attraction, right, between these 2. So it depends on the dipole. Okay, the more, this is a partial negative charge, but the more negative charge it has, the more it's going to attract this. Okay. Oxygen in a water molecule, oxygen is more electronegative than nitrogen is. So this partial negative charge is going to be a bigger partial negative charge than this one. Okay, and therefore it's going to attract the hydrogens more strongly. Okay. So we could say oxygen is more electronegative than nitrogen. Okay. Or the other thing you could say is, again, if you look at the diagram, the oxygen has 2 lone pairs So potentially it can form another hydrogen bond. So you just, yes, you get stronger hydrogen bonds in your ice, but you also get more hydrogen bonds because it's got two, whereas the ammonia's only got one lone pair. So, you wouldn't need to write both of these. It'll be one or other to get the mark, but I'll just put it here just because it's worth knowing. Oxygen can form two hydrogen bonds as it has two lone pairs, whereas nitrogen only has one. And it's always worth doing this extra bit, like don't just state something, don't just say oxygen makes two. Okay. Yeah, but you're saying why is it better than nitrogen? Because it does, whereas nitrogen doesn't. Okay. So it's always a good idea just to say, oh, and compare it to the other thing. Okay.